digital control, and then DR applications, which is of course at the edge, and then control architecture for that. We'll also do some OpenDSS based distribution system modeling and DR modeling and control and optimization using that. So uh, you can integrate actually OpenDSS with one of the cyber model tool, and in that way we can do a cyber physical analysis, and that part becomes cyber becomes next. So we talk about cyber infrastructure for distribution system, and as we integrate more and more digital devices network, that comes with certain vulnerabilities. So we'll talk about those vulnerabilities, CVE or cyber vulnerability exposures. Then we'll talk about some basic introduction of cybersecurity concept. What is cyber resiliency? How it differs from cybersecurity? And then we'll talk about resiliency metrics. So we can talk about security metrics also, and one of the ways to measure the cyber resiliency metric using multi-criteria decision making process. Then how do we model the cyber infrastructure system? That's where we talk about NS3 and Mininet. And there will be some demo demonstration with in my from my research group for OpenDSS and also NS3 and Mininet. Once we are done with the cyber and physical part system operation and modeling and analysis, then we'll be getting into some solution for cybersecurity. So there are multiple ways, like you can use even simple rule based to after you know the vulnerabilities. But with more increasing complexity, we will also talk about some AI and ML based technique, physics over AI, which can detect and classify anomalies in physical system and cyber system. We'll go through mainly focused on detection, because detection is the one of the first thing that need to be done for cyber security and cyber resiliency. If we cannot detect any attack or in the system or any anomaly, of course we cannot respond, right? So detection is very important. And then we'll talk about situational awareness, which is kind of next step, that once we detect, we classify, and we know that this is a cyber attack or even cyber failure, then why did it happen and what we can use that information, how we can use that information to enable resilience system, right? So we will go through that, and that's where we end the course. And hopefully we'll provide enough reading material so that you can continue learning a little bit more about each of these. Now, the motivation for this, which I am sure that most of you already know, um, is digitalization and integration of DERs, right? So as you look at the system, we used to have different kind of generation, right? Either it's nuclear or it's hydro or it's coal or gas or oil, right? And then we are adding a little bit more renewable, which is large scale, utility scale, which will be PV and wind and storage. And then we bring that power to the transmission system, which is at the high voltage, of course, after the transformer. And then we take those power to the near the cities and industry and commercial places. And then uh, all of these need to be monitored and controlled. So we have a control center for that, which is generation control center and transmission control center. Now, as we put more and more distribution system automation and also DERs, which is will be in distribution system, we will be also placing a new monitoring system, and which is like a distribution management system, and ADMS is kind of advanced distribution management system. But also with that comes the microgrid, which will be monitored by microgrid energy management system. And then DR need to be monitored by drums or DR management system. So system may change, and when we say before and after, It is, over last 30 to 40 years we are talking about, and now it is evolving pretty quick. um, and we need to make sure that all the goals for the power grid is still being met, right? So again, the motivation here is that more digital devices to control and monitor more number of devices that is being connected. And what are those? Those are mainly DRs, and which are helping us to form a microgrid, because without energy resources we cannot create a microgrid. And other than microgrid, distribution system itself for the DERs requires additional DR management system. Distribution system itself need advanced management system like ADMS. And we are hearing more and more news about cyber attack, right? So either you look at in US, or you looked at in India, or in around the world, right? So even Denmark, uh, and then Russia and Ukraine, right? So, and these are almost every week you'll be seeing that something has been compromised. Now, a lot of these compromise does not result into the impact on the grid, because there is another control center which we call Network Operations Center, or SOC, Security Operations Center. And sometime we have just the IT control, or IT Operations Center. And what they are doing is monitoring all these anomalies, and they are catching and they are isolating the attack which happens on the IT side and then comes to the OT side. OT side is the operational technology, uh, with the cyber system. So, which we will talk a little bit more about, because we're still talking about introduction. In this section, what we're talking about, our module, is why we are teaching this course. So with all these more and more attack happening on the grid, it is important that as we make our grid more automated, more digital, and more ready to take renewable energy and distributed resources, it could be battery, it could be electric vehicle. How do we make sure that we still keep it secure and resilient? One of the attacks that happened which really impacted the power grid outage was in Ukraine, right? Um, and it is projected that these number of attacks will keep on increasing, right? So, um, either you get different kind of graph, number of attacks that is happening, projected growth, number of vulnerabilities that we are discovering, which is called CVE, cyber vulnerability exposure. Those are increasing, and those are supposed to increase because we know that as we put more and more digital number of digital devices, it will come with its own vulnerabilities. Some are known and some are unknown. So we can only address the known vulnerability, not the unknown, right? Because unless you know that, you cannot fix it. So, and again, we're spending some time. The essence here is that number of vulnerabilities which can be utilized. What is vulnerability? It's like an open door and open window in your house, right? Which burglar can come in. So vulnerabilities are open window and open door in the digital devices, which will be accessed by cyber attacker. And as many as we know that we have, and we patch it, which means we close it, we will be more secure. If you don't know that there is something open, and why? Because we are not talking about a simple house. Think about a big, very big building with thousands and millions of houses and doors. I mean, doors and windows. And with that, sometimes you will not even know that which one is open and which one is closed, and some are secret. So as many as we discover, and we know that this number is increasing, is going to help us to make the system more secure. Other thing that is happening is the sophistication of attack, right? So we used to have, like let's say 20 years before, uh, we used to have a lack of collection for this information, right? Um, Typically, malware was not much, at least known to us. And then we got targeted effort by either by attacker or by state sponsored attacker to put several malware, right? So Stuxnet was one of those, and then several campaign to basically, like Dragonfly, Sandworm was also developed at that time. Ukraine was actually, just around that time was attacked, leading to the power outage. And then we had more sophisticated adversaries with ICS malware, like a Black Energy. So all these are, what's doing is that it's once it's get installed, it has to find a, one of the open gate and open window to get in the system. And once it's get in, and no one knows about that, it is software kind of thing, which will keep collecting information. And then when the time comes, attacker can use that set of information and set up that access to damage the system, right? So we had several different attacks during that time, which happened or compromised. And then now, till at least 2023, landscape has shifted. We now have a threat groups. So there are a lot of different groups, like Typhoon Old, which are making these malware, making these different targeted campaigns, and which means that more and more our devices are being compromised and more systems being attacked. So colonial pipeline, and it's not limited to only power grid, but any other energy systems, and sometimes banking, which will impact the system. So in this course, if you look at the landscape, that what we are talking, right? So we have this generation transmission, which is on the top, right here. And then we have a distribution system where the DRs are connected. And then we have some market grid, right? So microgrid management system. All the data from this distribution system or from transmission or from generation need to come through cyber infrastructure to control center, right? So these control center has different kind of software, which is basically analyzing the data and displaying and helping some control decision. And these software will be changing based on that which control center we're looking at. If you're looking at generation control center, you'll have a generation software, right? Typically that is applicable for nuclear because we don't have a separate control center with separate the whole management system being installed for, like, let's say hydro, right? And it's a different in each country. Some we will have a some personnel there at the hydro station, some we do not, right? Of course there is a coal plant and other gas plant might have a personnel and some software, but not as sophisticated as nuclear management system and transmission management system will be there, right? So we call it EMS for the transmission, which is typically looking at miles and miles, or several millions of kilometer transmission system. We have a DMS, which is also looking at a distribution management system of the distribution system once we come to the near the city or near the big industry plant. And that DMS or ADMS, and sometime that we used to have a OMS, which is a outage management system. In fact, that was the first one that came for distribution system because our goal was that how to minimize the outage. Now it has been integrated into the DMS first and then to ADMS. So ADMS has multiple different function and module, and OMS, which is outage management system, is one part of that. The cyber infrastructure, which is a small yellow cloud here, is really, really big, which means that it is all the communication link, all the digital devices, as soon as you take the data from analog and make it a digital, it becomes cyber, right? Why we need to do that? Because if you transfer the analog signal, it is more prone to noise and less flexible, right? And probably less accurate also in terms of sensing and everything. So to process the data and analyze it, we have to bring it to the computing, and computers in a different format. Like, so some are in running into the IDs, which is intelligent electronic devices. Some are running all the way till the computers, which is and servers, which is in the control room. And that's why we need to bring the data from analog to digital. And as the point when we make to analog to digital conversion, from there till all the way till it gets delivered back in form of digital control or translated into analog control, is everything is cyber, right? So cyber systems start with the analog to digital conversion, and then it stops when we convert that back, or we can directly give it to the control, right? So everything in between, sensing, communication, computing, are all cyber infrastructure. And of course, the lowest one is showing the management system, which is ADMS, EMS, DUMS, MMS, which is MEMS or microgrid management system. We call it SCADA, Supervisory Control and Data Acquisition System, which is one part of the cyber infrastructure to basically the whole infrastructure to bring the data and deliver it, right? With given that, which is very crude and very quick overview of the whole system we are talking about. Now, the first thing that we are going to focus is operation with DER. How do we operate the grid with DERs, right? Now, DER is connected typically in a distribution system at the low voltage, and they're small. If it becomes, and that's why you call it distributed. So it's a smaller and distributed throughout the network. It could take different form, which we'll talk about that later. But the first section is all about operation with DERs, right? Which we'll be spending the time, mainly today. And the next one, which will be tomorrow, we'll be talking about distribution automation, right? So that's the next section, distribution automation. Then third day, we'll be talking about DR application, DR modeling, and control, right? Fourth day, we'll continue talking about application and optimization and how to use that OpenDSS and some kind of optimization interface with that to do things to enable application. So that'll be fourth day. Now, fifth day, we'll be talking about cyber infrastructure and modeling, which is basically expanding this the part from conversion from analog to digital to sensing to all the way to communication network server, and what are the different part and where the vulnerabilities come from. Because once we know the vulnerabilities, which is a lot of effort, we know that how to patch it and how to fix if this get compromised. And after that, we will talk about some concept about cybersecurity, what it is, how it is defined, and then from there we will get to the cyber resiliency, which is kind of next step, that if once you make the system secure, and assuming that you can never make it 100% secure, because we can only do what we know, right? And if you don't know the vulnerabilities, but attacker knows, which we call zero-day vulnerabilities, then we can't defend much against that, right? So we have to make the system more resilient, right? And I'll talk about that more in detail, all of these. Then comes the resiliency metric, which I think is important, because if you say that the system is resilient or not, how do we decide, and how we can measure it, right? So we can measure reliability, we can measure security, we can measure stability in some sense. So we have to measure resiliency also. Is it perfect? Probably not, right? But so that stability measure are not perfect either. Then we'll talk about resiliency management system, which is a new paradigm, just like we talked about ADMS, DERMS, EMS, MEMS, which is another software to manage the resiliency. Then we will talk about AI, a very quick introduction, and how we can apply for cybersecurity, looking at event detection, classification, root causes, and that will basically helps in finally decision support and enabling secure and resilient grid, right? So this will be the landscape that we are going to spend in the next 10 days. And I think this is a quick introduction to the course. Any quick question about this before we take a 2 minutes or 3 minutes break and then talk about the first part? Any question?
Okay. So, we sometimes get confused the role of digital real-time simulators in emulating such kind of scenarios, like cyber attacks, detections, and all in the lab. Uh, Many people used to ask us, uh, like how much reality it can be to emulate the real systems, whether the 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 tested algorithms or some strategy in the lab will be applicable to the real time power or not. How we can answer this?
Yeah, so I was not able to hear very clearly, but I guess the accuracy of the test bed to model the cyber attack and in the system, right?
Yeah. Yes, sir.
Yeah, so it really depends that what kind of any modeling technique. It doesn't matter that it is OpenDSS, or it is RTDS, or it is OPLRT, or it's a Typhoon, or it's a PSAC or Power. Every modeling technique has assumptions. Those assumptions are that the way we are modeling and representing the behavior of the power grid, and which part of the power grid. So in the same way, for the cyber part, any modeling tool will have assumption, and those assumptions are the critical. Otherwise, we cannot solve the complex system. So it's a complex nonlinear system. If you want to model and analyze, you have to do approximation to second order, or some way of solution, so that you can mathematically solve it, right? So if you take the RTDS, it's a dominant algorithm, right? If you take the OpenDSS, it's electromechanical simulation algorithm. So every modeling tool has assumption and approximation, so that mathematically or numerical solution can be applied to get the result. And that approximation, as long as we are aware, we know that how far we will be from the expected true behavior of the power grid, or true behavior of the cyber infrastructure. And uh, and sometime you have to look at the what we are trying to model, right? Because each of these software has a capability, not only in terms of approximation and simplification that we did, but also that which behavior we are modeling. So for example, if you take the OpenDSS steady state modeling, then you are only modeling the steady state, right? Not the dynamic behavior. If you're modeling the dynamic behavior, or transient behavior, then you will be able to analyze that with, again, with certain approximation and simplification. Same thing for the cyber. So if we do the switching behavior or data packet, you know, going from point A to point B, you will be approximating certain behavior that happens in real system. uh, if you replace and do the hardware in the loop, you will be getting more closer and closer to the actual system behavior. So every test bed, every system that we do comes with approximation. It's all about, are we 90% representing the behavior that we want to? Are we are getting closer to 98%, right? It is never possible to do 100% because, if you look at the electromagnetic behavior, Dommel can do a really good job, but uh, not to the 100%.
Okay. Thank you, sir.
Yeah. So I see another one raised hand, and also in the chat, the high impact points of vulnerability of cyber attack in a typical distribution system. So we will be, I can answer now, but we will be also going first to talk about distribution system. What are the vulnerabilities point, and which is basically anywhere you put the digital devices. So substation, who owns them is also important. So if you have a third party business which are using that information, which is not feeding directly to the operation, it will have vulnerabilities but less impact. And there is actually the whole metric, and which we call CVSS, which talks about the different way of measuring the impact. We will talk about all of those things, in next few days. By next week, you will be, you'll have a better understanding of, if I answer this question. And the sensing feedback channels, or the communication channel between the control center and assets, will be also become very clear that which one has higher vulnerabilities. Communication channel are typically about access. It's not about having vulnerabilities, right? So anywhere where we are running the software, which has its own vulnerabilities, even hardware has a vulnerability, but hardware vulnerabilities are has to be done in the supply chain issue, which is not that easy to easy to attack and utilize, because you have to influence the whole supply chain issue. So software vulnerabilities combined with access control, uh, and basically decides the vulnerability that can be compromised in the assets. I see the next question. Do you have any standard or research towards the grid codes which consider the factor of resiliency to cyber attacks in the case of DR integration? I am not aware of any. Uh, there are a lot of standard for the DR integration, starting from 1547 to, from IEEE to several more from IEC. But looking at the standard for the cyber attack and cyber resiliency, there are standard practices which says or tells us that how to integrate the DER in a cyber secure practices. But the grid code for cyber resiliency is not there yet, and resiliency is about multiple things like weather resiliency or cyber resiliency. Those are two different things. So we will talk about more things, at least a little bit about that. Okay, now next question. I see the what's the impact of latency on DR cybersecurity measure. Um, in latency is not only the about cybersecurity measure. It's a cyber performance, which means that the ability to monitor the system and even control it is going to be impacted by latency. It it basically going to, it's one of the measure to even detect that something is wrong, right? If it is wrong by cyber attack causing that latency, or failure causing the latency, or it just more data that our bandwidth can handle is causing the latency. So it really depends on the root cause, but it is a performance issue more than a cybersecurity issue. Which cyber attacks are more dangerous? That's what we need to figure out through monitoring and control. Just like any failure in the grid, we cannot predict that which will be more dangerous in advance, because it depends on the operational point. So for example, if there's a DR connected and you're not using the power from that, then even if it's attack, it's not going to impact you, right? So it depends on the operating point at any given time. This is a very important question. I think, what is a prerequisite for this course, or you can search some literature to go through. This is a fast-paced course. We will start from scratch, and prerequisite will be some understanding of power grid operation. Cyber will be very basic, that we will be talking about here. And when we say prerequisite, basically I'm talking about ability to solve power flow, ability to solve and understand the uh, power system, some modeling. So we focus basically network modeling, so that we can focus more on DR modeling and control. And then for the cyber, we are starting from scratch. So, we don't expect much prerequisite for that. All right, so let's take a 4 minutes break. So I think I see, or maybe 5 minute break, and then we will start with the first part, which is operational with the DR integration.
Sure, sir. Sure. You please have a take a 5 minute break. Meanwhile,
Yeah.
we will discuss. Thank you so much. We will
All
start
right.
after 5 minutes.
Yes.
So I request the participant, if they want to raise any questions to sir, they can just turn on their video, so that two-way communication is also very important to making any system smart. No, so it will be good if you can turn on your video camera and then you can ask your question. It was also good that you can type your questions in the chat box, so that sir can read and he can reply. And one of the most important things that myself as well my students forget to inform all the participants, that attendance is mandatory for a certificate of this Gyan course. So I request Basu, uh, after this today's session, try to convey this in the WhatsApp group, so that the participant who have registered, as well as the participant from IT Jammu, they should be on online. Okay.
Yes, sir. Actually, we are also taking the list from the video here. The
Okay.
online link has given us to note down all the list
Thank you.
participants who have joined in this
Okay,
event.
you get the data when all will
Uh,
join. How many
yeah,
people? That's good.
yeah, yes, sir. We are taking the list of the participants who have joined us today.
Thank you. Thank you so much.
Okay, well, I think we can start with the next part. I'll
Yes,
share
sir.
the slide. Okay. Do you see the slides? Okay.
Yes, yes, sir.
Okay. Yeah. So we'll get through this in less than an hour next. So it's about introduction to DRH power grid operation, performance goals, and then how do we sense, communicate, compute, and control. Right. So this part relates to the one that I talked about. There are multiple section in this course, and the one that we're talking about is this one: operation with DER. So let's start from the beginning. So we have a generation, right, which has a different kind, starting from coal to hydro to gas to nuclear. And then we have this solar and wind plant. And then we basically put the step up transformer, take this power and to the transmission line, and then multiple different kV, which is different practices for the, I mean, if you look at the world level, we also have a DC transmission line, which is 1200
Vishnu,
kV.
Vishnu,
Okay. So if you're not asking a question, if you can mute, that'll be better. With the transmission, we get to the substation step-down transformer, which basically provides the power, then feeds to the distribution system, and then we give the power at different voltage level to sub-transmission customer, which is typically a large factory or industrial. And then there are some smaller factory which also get at the primary customer. This is the where 13 kV, at least in US, is the one that we also tie our like smaller battery and other resources to. And then we get to the secondary customer, which is like in 220 volt in India, and then here in US it's a 120, 240 volt, depending upon that which appliances we are connecting to. And then comes the DERs, right? So DERs are different kind. One is of course rooftop solar, which is on the top of the building. It Wind is rare, but it is possible, which we call community wind, which is connected at 13 kV, and that will be DER. Batteries, of course, which could be at the building level, at the shopping mall level, or sometimes installed at the hospitals, and so any building level batteries, houses to commercial to industrial, will be DER. EV chargers. So even though EV itself will be a DER also, but EV charging station is also a DER, because it is taking the power and can feed the power back, which is not happening much right now because we are not there yet. But eventually, we do have the capability, and it will happen, right? Which means that EV feeding the power back in operation. It is right now. It exists mainly as a demonstration or like a pilot project. Then we also have some generators, typically diesel generator as a backup, right? Sometimes gas generator as a backup. Again, depending on the technology and the preference for the owner, which is connected as a customer. It could be storage, which is thermal storage. In fact, in UK, we have a lot of thermal storage that is being used. A cogeneration plant. So if you have a biomass or those kind of things, that is typically cogeneration, but it does not need to be only that. Even the gas generation can become a cogeneration because of all the heat that you generate. You can use that for steam. So even the biomass with the cow dung and everything is also possible with the cogeneration. That will be DERs. Hydroelectric, not the one like a small river which is flowing through the city. You can make that as a runoff river kind of plant, very small. That's hydroelectric. Fuel cell, which is another kind of storage. And now even there is a modular nuclear, which is going to be connected, or at least in the pilot phase already connected. And that modular reactor will be the one will be also classified as DERs. So what is DER? Basically anything that is connected at the distribution level and almost at the edge. Edge means that we can't see beyond that, right? So that's the edge. If you even the demand response or smart thermostat can also qualify as a DER. I already talked about community solar, heat pump, water heaters. If it is helping with some kind of demand response, is also a DER. So definition of DER does not need to be the only which is generating energy, but also which can make the lower demand, right? This is like part of the demand response, or which can help with efficiency, right? So all these are some kind of distributed energy resources, because the net energy consumption is going to be lower by applying this technology. Okay, so with this DER in mind, and why This is important because if you have a demand response, it does require a communication link, it does require sensing, it does require control signal, which means that all of these need a cyber infrastructure. And without that, I cannot implement demand response. I cannot have an EV charging station being controlled. I cannot have a rooftop solar providing the power when it's needed. So all of these DR is coming with the cyber infrastructure. It's going to increase. So if you look at the global energy mix, let's look at the first left side. This is only showing the not absolute value, but the global change in electricity generation. Uh, you see the lot of green, and that green is a renewable, right? So this is from IEA. In fact, the newest report in 2025 that came last week, actually, right? So this is showing that overall, in terms of terawatt hour, the maximum change that has happened is in renewables, right? Net change is positive or negative. You can see that during the COVID in 2020, our energy consumption was going lower, right? And then because of that, and the net change was negative for the first time after a long time. But after that, it increased. So energy consumption was more, and then more, and then with some demand response, energy efficiency, it became lower. But it has been always going positive with some changes. And the maximum change that is happening is in this green part, which is renewables. Nuclear is constantly increasing. It decreased in 2022. It also decreased in 2020, nuclear. Gas, you almost see there's no increase in gas, right? And this is a global level. So in country level, it can. Coal, also, there's no increase, right? In fact, it decreased here and decreased here, right? 2021, it did help because of several different reasons. But the essence here is that renewable is increasing globally, right? Also, this is another IEA is looking at the million tons of oil equivalent energy, which is one way of to measure the energy. Uh, what it was in 2018 and what it will be in 2040. So you see the less change in oil, not much. It's not going to reduce, but not much increase either. Natural gas is going to increase a little bit, 3,500 to 4,500. Coal is going to decrease, right? Renewables, that's the maximum change, 4 times, right? Now, energy in renewables is still less, right? So this is looking at the absolute, not only net increase. Uh, this is a huge increase in renewables. Bioenergy is going to increase, nuclear is going to increase, and so that biomass is going to, almost be same or slightly decrease, and hydro is going to increase also. So as it's increasing both, right, utility scale and also DERs. As it happens, the maximum operational challenge that happens is which we call duck curve, which is getting more and more deeper valley, right? So why it is happening? Because, and this is from California ASO, which is one of the past graph from few years before. But what is showing that over the year 13 to 15 to 20, the valley has been basically going more and more down, right? So what happens that if you look at this hour, around late afternoon, which is this 2 p.m. and this 3 p.m., more and more solar are producing maximum power output, which is like late afternoon. And once it does, then your energy consumption or power consumption will go down, because you will get the power fed from the solar, right? So that's why there's a drop. But in the evening, around 5 or 6 p.m., when the sun is down, all those PV will be gone and the load will be increasing a lot, right? And the ramp rate will be really quick, because everyone is going back to their home at 5, 6 p.m., or they're already at the home if they're working from home. And so the power consumption is going to increase anyway, because those are the peak we have. But because the PV is going to go out, you will have a higher jump, right? So this is another impact on operation and handling, that how do we handle first the drop and then this ramp rate, which is a more bigger problem, because this is a big ramp. This is operation problem with the DR, and that can be implemented only with the cyber, right? uh, because we need to communicate with DRs. So what can we do? There's a lot to do in terms of monitoring the grid and looking at this operational reliability issues, controlling and protecting, understanding that these DERs are very diverse, just that we heard in the last slide, being from demand response to EV charging station to even the modular reactor with the nuclear, right? And storage, which gives us a lot of flexibility, and that makes it complex to control. Designing and planning, which has to be done in the long term, is very much needed. Investing in that. This is from PCERC, which I was one of the report writer. And then all of these, which is very much related to this course that we are teaching, is educating the engineering workforce about these things, right? And then other thing that we can do is economics, right? So economics and market. How do we use that to control and provide enough incentive to help the grid operation? This is a little bit more about detail, that if DER happens with unintentional islanding and we don't are fully aware of that, it's very dangerous, because DR will be feeding the fault, right? Which was not possible if the DR was not there. And because if it's a feeding the fault, it is safety issue. It is so protection need to be taken care of that with the DR that happens. Two-way power flow, again, a similar issue. If you isolate from this side, you don't guarantee that there will be safety for the personnel who are working on that. Power quality issues with the DERs, because a lot of power connects non-linear power draw. There is a multiple configuration that is possible with DR. It will increase. Crew safety, I already talked about, with the backflow of power, and how do we detect and isolate them. And then comes the power system protection coordination, because protection need to take care of the newly added DERs. And then missing link between the EMS and DMS. And also I can add, now DUMS and MEMS, right? Because transmission grid and distribution and macrogrid is all connected with, because DR is feeding into the distribution and microgrid. But also the impact is very well reflected on transmission, right? Because if you have a more and more distribution feeder with a lot of DRs in the evening, when it goes down, if it's a PV, wind probably will not go. In fact, it will increase, but we hardly have much wind in there. What will happen is that the transmission need to transfer suddenly more amount of power during that time when your all the DRs is going to die out, because there's no solar. And that means that the EMS and the communication and the information exchange with the DMS, our distribution side, our microgrid side, need to be more and more for the control and operation. Voltage regulation, with the increasing DR is more challenging, because We typically used to have that voltage will be high at the substation feeder, and it will go down as we, because there's more load connected, and we can control that from the feeder, right? Then we put some cap banks in a capacitor, and then we feed the reactive power, or basically balance the reactive power, so that we get the voltage good. But with the DRs, when it's feeding its own power and maybe reactive power, uh, uh, you know, controlling from, there will be more control variables basically, right? And voltage regulation is more challenging. That how do we set? Cybersecurity, which is a topic of this course, is going to be more and more uh, challenging with more and more data points and more digital devices. Number of control variable will definitely increase because we are adding more and more devices with that DRs. And then this large number of control variables to solve, and also this valley and dip that we just talked about. Lack of visibility that comes with that, especially for the operator, right? So if the DRs are owned by customer or third party, then the grid operator cannot control it, which will be typically the case, right? So if a business, if a shopping mall owns a DR, then like they will go through the contracting through the third party, uh, and uh, and they will be less visible to the utility grid operator. We do want to maximize the value of all the DRs, including the storage, and especially with the four quadrant operation, it becomes more complex, right? And when we say complex, it means flexibility and number of control variable that we can allow to change. Resiliency versus economics versus reliability assessment, and then automation and asset ownership is need to be considered. Automation brings the cyber part also. Other thing is that we can see, because these DR are not, at least most of the DRs are not dispatchable, right? Which means that you cannot control to dispatch as much as power you want, right? One example was this. If you look at, like let's pick this solar eclipse, right? So when this happens, it brings another uncertainty on the solar output. So this was from 2024, but there was one which came before that. This solar eclipse path was more towards in a Pacific Ocean. But if you pick another solar eclipse, which happened before that, that did impacted solar output, and with that there was frequency problem. There was a of course the voltage problem that comes with that. So now we get into that with all these DR being connected and multiple challenges, which mainly impacts distribution but also transmission. What is the our fundamental operational practices? So it doesn't matter that we look at the transmission or distribution, with the houses with the DRs, with the building DR, you have a distribution, and then we have a transformer, and then finally from there to transmission system, and then to the generating plant, right? um, the only way we know that what is the status of the grid is by sensing, and by sensing means we put sensor. So the most common sensor that we put is a current transformer and potential transformer, or CT and PT, which is different size, different rating. uh, with that CT and PT, we can also use that information to feed into the phasor measurement unit, or PMUs, which is much faster, much synchronized, and better high resolution data to analyze if you're especially looking at the dynamics. Same thing you will do with the distribution PMU. which will be in distribution system. You'll put the smart meter, which is a little bit slower to report. And all these things, when we say slower and faster, it depends on multiple things, but two things which is more important is that sampling size of that sensor and the communication that can bring the data, right? So the sampling is, like smart meter, actually, it can sample really fast, right? It's local there. And so that the CT and PT, because which is analog signal, and give it to PMUs. But the communication link, which is bringing from smart meter, we don't configure that to give us fast rate of data. So it is not giving us fast rate of data. Sometimes it's a day delayed, right? Uh, but PMUs, we do put communication link to bring the data, and that's why it's fast. So once you sense, you collect it locally, which will be in one of the boxes here, or one of the control room here, which is a substation. First collect it locally and then communicate it to the server room, which will be feeding the data to the control room, right? Control room again could be nuclear power plant, could be whole transmission grid operator, could be reliability coordinator, which is one step above, which could be ISO, independent system operator, which is for the market behavior. And for distribution, it's a DMS. For microgrid management, it's MEMS, microgrid management system. And the new concept, which is cyber resiliency, it's a resiliency management system. And same way, it will be, for DER, it's a DERMS. So a lot of these software which we install at the control room, depending on that, what we're trying to monitor, transmission, distribution, and generation, and microgrid, or DERs, or cyber. So cyber will be done in the Network Operation Center, NOC, or Security Operation Center, SOC. What we do with that, once we get to the system, our two main thing that we want to do is situational awareness, which means that how good we are in the system status. Are we operating it well? If everything is good, or we need to interrupt and do something. And when we say we need to interrupt and do something, that's what is decision support. If everything is going fine, is operating as is expected, then status is normal. We don't need to control anything, right? Of course, we assume that there's some autonomous control, like a protection, will do its job without any prompt from the control room. And so that there are some other autonomous control for frequency, voltage, which will do its job when the time comes. There are also remedial action scheme, which will also work and take control as needed. But with all these, we need to make sure that those control that is happening is also being reported. And that's what, if those operation, like let's say protection operated, our sensing will bring the data too. That line hasn't been isolated, or this DR has been isolated, or this generating plant has been isolated, right? So as this happened, situational awareness is all about knowing what happened in the system. And decision support is about making a right control action to help the system move back to the normal. Okay. To determine that what need to be done and control signal need to be sent, the first thing we need to do is predict. We predict load, we predict sometime pricing, we predict the solar output, we predict the wind output, we even can predict the operation of storage, we can even predict the electric vehicle movement and how much charge is needed. That will help actually with the load forecasting. So prediction is very important. Without prediction, we don't know how the load is going to look like and how much we need to generate. So even in the normal operation, we need to make sure that generation is going to match with the load. And we do it in different steps. We predict for the day, predict for the hour, and then we are ready to generate power as much as needed. And that's what is called planning. So, matching the generation to with the predicted load, with the predicted solar, with the predicted wind, and others that we can predict is going to help in planning. And this planning is short term planning. Of course, there is a whole part of the long term planning, which is like a building a new generation plant, building a new transmission plant, or planning for the fuel purchase. Like if you need more coal, more gas, you need to plan for it. That is done by the generating plant. And then comes the main part that we are talking about, which is operation, which is we already talked about sensing, communicating, computing, and then visualize. So once we compute, we need to show it here, right? What do we compute? We'll talk about that. And then finally, who will pay for it, right? So it all of these has to be paid by the customers who is consuming the energy, and that part billing is done in again in different ways. Some are market participant and the billing is done differently, and some are non-market, so billing is need to be done differently, right? So this is again operational philosophy of sensing, communicating, computing, and control with the same goal. And the goal here is that be reliable, which means that keep supplying power. uh, Economic, do it in the minimal cost. In market, it's slightly different. Secure, which is a concept of keep operating normally even with the limited failure, which is one component out or maybe two component out. Efficient, which means that minimize the losses, and be most efficient possible means that use all the energy available in a way where it is needed, right? So minimize the losses. Resiliency, which we'll talk throughout the course, and then we have the whole thing, is about three things: that ability to withstand, which means that cyber attack is happening or weather impact is happening, we should be able to withstand, which is comes from the design and operating the system in that way. Second is recover, that once the event has passed, how soon we can recover, right? And third, which is a little bit more tricky, is related to this predict, which is anticipate. So how we can anticipate it in a better way, that we are better prepared to withstand and recover, right? So that will be resiliency, and these remains the objective. Doesn't matter that we talk about transmission or distribution or microgrid, or even the nanogrid, which will be at the lowest building level. Okay, let me see if there is a question so far. Okay, if there is no question, we'll continue.
Hello, sir. Am I
Yeah.
audible?
Yes.
Sir, how this resiliency is different from security?
Yeah. So we'll talk about the whole class
Yes,
in future. The shortest is that security is about like let's say you have a home with hundreds of doors and hundreds of windows.
yes,
So
sir.
security is about closing all those door and window and controlling it in a way that no one can enter which you don't want.
Sir,
Okay. While
yes,
resiliency is about that, which means that no one can enter. uh, at the same time, if someone can enter, they are confined to only a small area in the building. And Third, even if they can enter and not able to confine to the small area in the building and they damage, then how do you identify and close that, basically either destroy that door or that window and minimize the impact on the rest of the building. So that will be resiliency, right? So security is only about securing it, which means that stop intruder in that building.
Yes, sir.
Okay,
Thank you, sir.
sure. So there's one more question. Proper monitoring such as awareness of the DER integrated grids are of importance nowadays to make the operator aware of the regular operational scenario of cyber attack. As distribution system state estimation is getting prominence to monitor this DER and this distribution. Okay, so question is what is the current global scenario in the context of practical real-time deployment of these estimator in the control center? So state estimation is going to give you first set of anomaly, but if you look in point of cyber, it is only going to tell you once the cyber attacker is already in the physical system, right? So state estimation is helpful to see the impact on the in the power grid, but not um, in terms of detecting that even when they are in cyber, right? Because that's a better way to do. In terms of deployment, almost at least in US, all the control room for distribution does have a state estimation, depending on the size. So if it's a large distribution system, they are running state estimation. In terms of very small, they are not running a state estimation because they don't. They have more issues because uh, if you don't have enough number of sensor, you cannot do the state estimation, which is typically the problem with the distribution system operation. Uh, and you need to aggregate the information to do the state estimation, which that's what even the larger distribution grid operator do. When we will get there that we have enough number of sensing and make this work, it depends on that we don't even know the network all the way till secondary houses, right? So network is typically not known once you leave the transformer. And I'm talking about the secondary transformer, which feeds to the 10 or 4 houses. So in terms of practical deployment, yes, most of the larger distribution grid operator already have that. But in terms of how good and accurate these are, I think that is not even more practical because the network is not fully known. Sensing is not enough there. So we are still operating the distribution system operation, with the state estimator more with approximation and aggregated information. Just like you in transmission, you aggregate the whole distribution system as a single load. Next question, state estimation is still prone to cyber attack like FDIA. So can we fully secure the state estimation process? Yeah, so nothing can be secure. So that's one thing that I want to make sure that you get, that there's no 100% security possible. Now, false data injection, FDIA attack, is something that is, at least I think, is, when we talk about cyber attack, we look at the probability of that attack and impact. So there is a lot of impact, but probability of FDIA is very, very low, very low. Why? Because you need to know a lot about network and system, which is not available in public domain, which means attacker is not available to either. Attacker only do that if they are internal, which means that they are already working in the system and have enough information to do a FDIA attack. if they can take an effort of knowing all the information and do the FDI attack, they can also launch an attack which is more powerful and more easier. So for an attacker outside, FDIA probability is very, very, very low. Okay. So how do MEMS and dumps? Thank you. How do MEMS and dumps differ? So MEMS is only for microgrid, right? DR is for DR, right? So DR would be typically in distribution system, because if it's all DR is in microgrid management system, then MEMS is already monitoring that. So we don't need to monitor that in dumps. While DR management system need to look at the DR, which is in rest of the distribution grid. So those are the two difference. MEMS full form is microgrid energy management system. FDIA can be part of more enhanced set of attacks, including spear phishing. I think it's a lot of different concept here. Spear phishing is a very different to get into your, I'm talking comparing that with the doors. So phishing is an effort to get the first foot in, which is very different than the launching an attack with FDIA. But it could be, yeah, like I said, that it could be one of the attack which is impactful, but with the lower probability. Stuxnet was very different, which was basically delivered through a USB and installing a malware, right? While if you cannot physically go and install a malware, then we need a access point, and that's what is typically done through phishing. Okay, so let me go back and try to.
Sir, I had a question.
Yeah.
So basically, are we going to talk anything like or discuss anything about the building of real-time test bed?
We will talk about very briefly, but
Okay.
we'll spend more time on OpenDSS and Mininet testbed.
Okay. Okay. Thank you.
Okay, so we will go back to continue talking about introduction, and I think we have maybe next 15 minutes I'll talk, and then we can stop and then do the continue next day, which is tomorrow. So this is talking about more power system operation and expanding on situational awareness. What does it mean and how it is possible with the goal of economic, reliable, resilient, secure grid. SCADA, which includes sensor, which we already talked about, CT and PT, current transformer, potential transformer, PMUs, a switch status, which is also we need to get that information. Switch status is directly not coming from the switch, but one of the sensor, which has to be digital. So relay can tell us that switch is open or not because it's already connecting and talking to the circuit breaker. RTU, which is remote terminal unit, which collects the data and bring it to the control room. PDC, which is a phaser data concentrator, it collects the data from PMUs and bring it to the control room. Merging unit, which is basically merging a lot of digital signal at the control substation and then sending all the information in digital format to the control room, right? So all have different objective with but basically for sensing and collecting data. And then we have a communication network, which is several different kind. We will dive into that what are those different kind later, maybe on fifth day. And then we have data archival historian, which collects all of these information locally at substation, and then at the control room. Now, when we say this substation and control room, of course, these are the two most important data collection point at the lower and bigger level. But there is also some data collection point which happens along the grid. And when we say along the grid, then we are assuming that cyber is following similar architecture, and then at some of you know data point, it is being collected locally at like a pole top or like a ground station, and then being fed to the substation, then being fed to the control room. So all these things exist, but everything together will be a part of SCADA. The first thing we do once we get the information is state estimation, which is basically trying to estimate the state with that set of data, right? So another way, state estimation is trying to fit the measurement into the physics model of the grid. Why? Which is a very good thing about power grid, that all the measurement has to follow a certain rule. If one measurement is off or compromised or attacked, I can detect it using fitting into the physics model. So it's like you got 2 points and you're doing the line, right? You can easily do that because you can always find a line which will fit into the two data point, right? Or two points. If you have three, then you may not fit a single line into that, right? If they're aligned perfectly, you'll fit it. And in a state estimation, we know that all the measurement, if there is no noise, there's no delay, and there's no compromise, it should fit perfectly into my physical system model. Just like 3 aligned or 4 aligned or 5 aligned points will fit into the line, right? Of course, if it's not line, it can fit into the curve, like hyperbolic curve, right? Same thing for state estimation, should fit. But we know that there is a communication loss, there is a delay, there is a noise, and that's why measurement may not be right. How do we know that which measurement is not right? By trying to fit into that big curve, which is driven by physics of the grid. And if one of those data point is not fitting, we know that this is the one which is wrong or incorrect, and we can estimate it, right? Or we can fix this. So state estimation is basically a process of fitting my measurement into a system model, which is a physics-based model, and trying to re-estimate. Re-estimate means that measurement will match with estimate if it is a good fit. If it will not fit into that measurement model, then it is a wrong set of data. Assumption here is that most of the data is right. Because if the most of data is wrong, then state estimation is not going to work. Okay. Now, the next part we do is that after state estimation, we do power flow and other things, and then we display and organize that information. And then we use that to send alarm. Alarm is that, okay, this substation has higher voltage than it should be. This line has a more power being transferred than it should be, right? So those are alarm and alerts that goes to the substation engineer and control room operator, and then from there it goes to the crew so we can fix it. So once the situational awareness is done, the next part is decision support, which is looking at the real-time operational, short term and long term. In short term, we are talking about different time frame, right? So we're talking about milliseconds, seconds, and maybe minute. Then once we get to the real time, we were talking about milliseconds, seconds. In short term, we are talking about minutes and hours. And then in long term, we are talking about day and months. So OPF, which is the, after state estimation and then power flow, we do the OPF. Why OPF? Because it has a control variables, and that's why it can help with the decision support. It will give me what control to take. So first thing we do, which is in day, and hours is unit commitment, which tells us that which unit should be on, which unit should be off, so that we can match the power load with the energy generation. And the power load need to be forecasted and known. Then we do in minutes economic dispatch, which means that once we know that this unit is on, how much power to generate using that. And then we know the hydrothermal scheduling, which means that hydro, we should actually maximize it if it's possible to use all the water, and all the constraint from agriculture, from fishing, from like all the hydro constraint that can happen is taken in this hydrothermal coordination. And then we do the security analysis, which is OPF is again running in minutes, giving us control variables. Security analysis look ahead, that what if this goes wrong. Now in the power grid, which is biggest power made, basically man-made or human-made, biggest human-made machine ever, we want to make sure that that all the component that can go wrong is considered for security analysis, which is not possible because we have thousands and thousands of different component in the grid, which including just the transmission line and generation. So we have to select that which one we want to analyze, and then from there, that list, we say that if this happens, if this goes out of the grid, can we still operate normally or not? Then we do the load and price forecasting. Then we do the energy interchange. Energy interchange, basically looking at different areas, how to exchange the energy. And then we are looking at the market power analysis, right? So market power analysis is, and this is not a complete list. So market power analysis is looking at long term in an electricity market operation, that if one generating company, because there are multiple generating company, is influencing the market operation more than others, right? So that's the simplest definition. And then looking more deeper into operation, so automatic control is uh, is very important, because those things we are not making a decision, but it's already happening in the field, which depends on, first one is protection, which is the fastest one. In few cycle it has to operate. Typically it has to detect the fault in half cycle to one cycle, or maybe max of one little bit more than one cycle, and then it has to wait for a few cycles so that it does not mal-operate, and so it's the fastest automatic control. Then there's a droop control, right? And we are talking about those things that we have made. There are other things which is faster than that, like a wave propagation, like electromagnetic current flowing into the from generator to your distribution. That's much faster, right? But we can't control it. So we're only talking about the fastest control, which is the protection. Then there's a droop frequency control, which is looking at installed in generation, and it is trying to control the frequency as it sees that real power need to be changed to fix the frequency. So droop control is basically responding to the frequency increase or decrease by changing the real power. Then there is the AVR, automatic voltage regulator, which is monitoring the voltage and changing the, basically a lot of different things. So one of the things that will change the field current in the generation plant to make the voltage control. And AGC is automatic generation control. It is looking at the real power and changing the fuel injection to increase the generation. Then there is a RAS, which is remedial action scheme. There is under frequency load shedding. So these are all automatic control, which is, of course, we need to decide where to install and when to install. All of these are looking at the voltage, frequency, and power flow. A little bit more about AGC. So AGC is the online computational tool, which we are looking to control the generation in automatic control by looking at the frequency and also net high line interchange. So net high line interchange is between the two different areas. which looks at that how much was planned from this control area, which is one of the area in the power grid that we decide on the boundary line. Typically, it will be like a, you can think about like a state. So one state is tied with another state, or one interconnection is tied with another interconnection. Also, you can look at that owner of the grid, which may be going to two states, right? So you can say that UP is one of the state, and basically neighboring state will be MP, and if it is owned by two different, which is not the case here, but if they are owned by two different operator, then they have to decide that how much power will transfer from UP to MP. And if it is more than that, I need to control it. How do you control? By redispatching generation. And how you implement it, you through the AGC. So tie line basically allows area to rely on each other when it's needed, and especially under disturbance, it will automatically increase or decrease the generation. But AGC is a control mechanism, right? So it's a mechanism to increase and decrease the generation, which can also take the control command other than being automatic control command from the control center. So what it responds to automatically is ACE, which is area control error. It is looking at the actual frequency and plant frequency. Plant frequency is typically 50 hertz in there. In US it's 60 hertz. And then we need to estimate that how much megawatt should change based on the frequency. For every system, it will be different, right? So you can look at that typical historical response and decide that how much frequency is going to change if I increase the generation by this much or decrease the generation by a certain percentage, right? So based on that, you can decide the beta and then can set this in the equation. Sigma pi is a megawatt flow out of the area in this, which is basically we're talking about if UP is connected with MP with these two states with 4 tie lines, and each tie line is pi is going on one line P1 and then P2 and P3 and P4. Then if we sum it up, then we'll know that how much power flow is flowing from one state to another state. And then we know that it should be less than 200 megawatt, but it is flowing like 300. So find the difference, and which means that we have to minimize generation in one area or one state by that much difference, right? So that we will reach to the targeted value. So this ACE or area controller is calculated in that way and then implemented by, again, you can increase the power P or decrease the power P only by controlling the fuel injection, right? So that's what we do to maintain it. Just a pictorial view of that. You have the frequency difference right here. Then you have frequency bias, which will give you B delta F. And then we have the tie line, which is tying two different areas or two different state or two different utility boundary areas. That will give us P tie, and then we know that how much should be. That will give me delta PTI, and that will be ACE or area control error. We can do the filter to smoothen out for the noise, and then feed it to economic dispatch to find out the 3 different P dispatch. If we have 3 generation, if we have n number of generation unit, we will do the all n. So talking about the states, different state that we can operate, normal is where with the load is met, the good voltage and no overloads and minimum cost. We can, if one things fail, we can go to the alert, or without load suddenly increase, or that also will go to the alert mode, where most of the load are met, but there are some over voltage, under voltage problem. There are some short-term overloads and minimum cost. Typically, this happens keep on happening. I mean, we typically are in alert and normal mode very often. We want to go back from alert to normal as soon as possible by controlling the signal. If we don't control it good, or something happen which will cause the alert to go in emergency mode when there are severe voltage problem, load largely not met, a lot of overloads. At this time, cost is not a concern. So we want to first fix the problem and then focus on economics, right? So security is more concerned, or reliability is more concerned. If you don't do something here, then it becomes a quick progression to the blackout, where most of the load is lost. Cost is not concerned anymore, but restoration is, and then corrective action is there but limited. From there, you cannot directly go to the normal mode. You have to restore the power first, then slowly try to go to in the alert mode and then go back to normal. We do want to be always here, but we know that we keep switching in between throughout the day, and this is something we want to avoid. This is something that happens rarely, but and then we need to use that to restore the power. So let me go through quickly, very quickly, through multiple different events to talk about these things. So if you think about different events that happened in the past, so this is a famous 1996 blackout, which happened in Western interconnection of the US. It always start, you need to focus on how it starts and what are the signals that I can detect to fix the problem before blackout happens, right? So in this one, it started with one of the line contacting a tree, right? And once that happened, that line goes out, and that will basically lead to another transformer being out of service. So that happened, 2 lines out, and 5 lines were now out of service. It removes hundreds of MVR for transfer, right? So initiating event is that 1 or 2 line going out. Typically 2, because 1 line we should be prepared. And then that will result into multiple things going out. So generator will go out, more number of line will go out. There will be some signature to look for, like oscillation, if you had a real-time monitoring of that. And then oscillation will reach at the peak. If you detect this early, we can take a proper control action, not any control action, but the good control action. It will avoid the blackout, otherwise it will happen, right? So blackout happen in many states. Second one, which is the biggest here ever happened in US, is 2003 blackout, which includes the Canada. This also started with something else, which is state estimator not giving you situational awareness, right? So First Energy turns off the state estimator because it was not converging, and then something happened and they didn't know that, right? So one generation went out, then one line went out, and then again it started with the tree, right? So that's is very common thing, and that resulted into multiple different things. If I can detect these things, low voltage, high load condition, so these are the things to watch for before the blackout happens. And that was again the biggest blackout, which took more than 50 million power output. Another one which is very relevant to this cyber security is Ukraine power outage 2015. It started with phishing attack on multiple different employee of the company, because employee is the only one which has access to the operational technology side, or in other way, cyber infrastructure which is operating the grid. You cannot access it from outside, right? So cyber infrastructure for operating the grid should be secure and not accessible. It should not be on internet. It should be on intranet. So that means that to get to the cyber infrastructure of the power grid, you have to go through a person or someone or device which has access to the operational technology, or OT. So this started with phishing attack on multiple, if you send 100 to 1,000 employees, if one click on that, you got one door open. That person had access to IT. That's why it was accessible to by attacker. because you check the email, and also has access to the OT side. So from here, uh, attacker was able to get into the computer because this person clicked on a link in email that they should not be, and that's how the malware was installed in the computer. And from there, it was trying to collect information for 6 months to 9 months, and that information was used to get into the OT side, which is the operational technology of cyber infrastructure. From there, they just open multiple different breakers to take the multiple different line out, and that resulted into a basically power outage, right? Of course, there is a lot of firewalls and everything in on the way, but from here, from email, the link was clicked, that resulted into malware installation, that resulted into the access to the corporate network. From here, it resulted into because from this path they can't reach, attacker cannot reach it because this is access controlled. So they need to go through this path, and this is what attacker took to reach here. And so this way that resulted into a cyber outage, cyber caused power outage. A lot of steps here that was happened, with finding email, right? So that's the first thing you do. That how do I find email of the employee? That is typically available, and then you can scrap the data from internet, and then you got a lot of email. And then email was sent to thousands of employee. One of the employee clicked on that link, which resulted into the remote access Trojan, install Black Energy 3 by embedded Visual Basic script, which of course email will not show it. And from there, attacker was able to gain access over several months. And then from there, it was able to look at other password and different log information of the key and credential and collect that. Once they collected, they were able to send it out through the IT network to the attacker. And then from there, they were able to get into the HMI, which is human machine interface, from there to DMS, distribution management system. And from there, they were able to get into the substation devices, which is RTU here, and from there to the breaker. And once you get to the breaker, then you open multiple breaker and opening the line, and that resulted into a outage of 225,000 people. So that is one example. Other outages that is happening is also has a similar trend. May not be the cyber attack. So 2012 was the biggest, in fact, the biggest world, biggest outage scale, even in the world, like how many people were impacted. So in 2012, it was other condition like high demand, low monsoon rains, failure in the transmission system, which was started the first one, Bina Gwalior line, circuit breaker. And then from there, it basically forced the power to travel through the eastern region and then causing higher transmission losses. It's very similar to the Northwest 2003 blackout here in US. And then led to the frequency loss, and then multiple circuit breaker operating, right? So again, what is important here is that one thing is causing, second operation, which is cascading, which we call it cascading outages, and that resulted into a big outages, right? 2024, which was last year, Ecuador, basically had the similar issues with 18 million resident, impacted. That also started with transmission line that went out because of fault, and that led to cascading disconnection across the national grid. In Cuba, in October, something similar happened, where 10 million people went in the dark. That started not with the transmission line, but one of the thermoelectric plant, which is one of the largest power plant in the country, also in Cuba, and that resulted into a again cascading effect, leading to another generator outage and another transmission line outage, and they were able to detect and fix the problem in 24 hours and restore the power. One thing which I wanted to point out, that it does not need to be cyber or cascading because of dependency of each other line, but also weather impact. So September 2024 in eastern USA, we had this big hurricane Helen, which went across southern east United States, and that resulted into 4 million people power outages as it went through this path, which was a category 4, which is not very high, but it's still very high. And that also resulted into a lot of economic damage too, right? So different cause of event starting, and I call it butterfly effect. It's on YouTube if you want to watch this video. What does butterfly effect means? That basically it was chaos theory, which says that a flutter of wings, a butterfly can start a storm somewhere else. Similar thing happens in the power grid too. It is all interconnected: distribution, macrogrid, transmission, generation, DER, all are connected, and the load too. And any disturbance can scale up because one disturbance impacts other component impacts the next set of component, and that's why it's called cascading. And that complex system problem is can be initiated by anything, either it's a flood or superstorm or wildfire, heat waves, fuel supply shortage, or cyber attack. um, so maybe we'll stop here. Let me know if you have any question, and we'll continue tomorrow. So I see another question. Can we do core simulation using OpenDSS and S3? Yes, we can. We will talk about both OpenDSS and S3 separately. Even though in our lab we use OpenDSS and Mininet, but you can easily do OpenDSS and S3 also. We will not have enough time in this 10 days to do a simulation and do a home exercise for that, but we'll be in a very good shape after demonstration so that someone can do by themselves. Okay, yeah, so looks
Sir,
like there's some question. Yeah, go ahead.
his distribution system, DER's state estimation is complex when compared to the normal state estimation.
Yeah, in terms of complex, that we don't have a full visibility of distribution system. Network is not fully known, and so that a lot of load point. While in transmission, it is fully known. We do have enough information about transmission, and that's why state estimation is more accurate and less approximate and less aggregated compared to distribution system.
Thank you, sir.
So I see another raised hand from Satya Sai Chandra. Yeah, go ahead and ask question.
Yeah, thank you, Professor. This is Dr. Satya from Hitachi Energy, R&D.
Yeah.
So I just have a question which is in the context of a microgrid. So if you have a typical microgrid with, let's say, number of assets, be it solar, battery, or diesel generator, anything, you have integrated that to the grid and this setup. So you have the sensing, as well as, as you mentioned, you have an RTU for communication and other layers of control on everything.
Mhm.
And then you have a EMS, energy management software, or system or software in the microgrid context. So in this setup or in this template, where do you see the scope for a cyber attack? Because mostly it is all wired or kind of an wired in interlinks, or you can say in that way. If because even the EMS software generally people provide or companies provide on on-premise as an on-premise software or solution. Yeah.
Yeah, so each RTU or the merging unit or even protection device comes with vulnerability, and those are like which we call CVE, which we'll talk about on fourth day with example. Like in fact, some of those are public available. Those CVE is the one which can be compromised by the attacker. And then even if it's a wired or wireless provides additional way to get the information, but wired is more secure with the access control. But if the vulnerability is compromised and this is connected, so you can think about just like electron will flow on the wire. If it's connected from node A to node B, same thing will happen for the attacker who has compromised the vulnerability in device A. If device A is connected to device B, they will get to device B. If device B is connected to device C, then they will get to device C. So irrespective of communication network, once they get into one thing, because of vulnerability, which is open door and open window, they can get to the other device, and that's how they can compromise the operation.
Yeah. 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 Thank you. So maybe we'll have more sessions on this. Let's.
Yes, yeah. In fact, we have not even started on the cyber and vulnerability part yet. That will be fifth day.
Uh, so thank you. If you have anyone have question, uh, or we can close the session today. Uh, okay.
Yes, sir. One last question for me. So DERs means we have to use so many power electronic devices for converters for connecting to the grid. So is there any effect of reactive power on the grid?
Yeah, so reactive power, active power, frequency, voltage, all are correlated, and each change in any of these will impact the others. In our power grid, the two objectives are that, well, the primary objective is to balance the real power and balance the reactive power while keeping the voltage and frequency under control and desired. So with the power electronics, it can inject reactive power, it can convert real power to reactive power, and that's what it makes it complex, but only if you allow it. So if it's a grid following with a certain control mode, which we will talk about all of those DR control mode uh, in third day and fourth day, no, third day actually, uh, that will decide that how much power we can inject and how much reactive power we can inject. So even if the mechanism exists to inject the reactive power, if you don't allow it, it will not be possible to inject and control. If you allow it, then we need to monitor and control from the control center, which makes it more harder, or control it through automatic control. So the question, I think the answer to this question is complex because it depends on the control type, it depends on the control allowance, it depends on the communication that will allow us to control or not, it depends on the ownership of those DRs. So a lot of those things that goes into the need and ability to control the DR to help with reactive power are not even allow that to help with the reactive power.
Sir, I would like to ask one question that when it comes to the mathematical modeling of all the DERs and cyber attacks and all of those things, so can we do with MATLAB or we need to go for some other software, sir?
Yeah, MATLAB is possible. It depends upon that what behavior and we want to model, right? So if we are modeling the steady state behavior, I think MATLAB can do a good job. If you want to model certain dynamic, MATLAB is also still okay. But if you want to reduce the time scale and looking into the transient behavior, MATLAB is not so good, right? So then you can do this at Simulink. Then Simulink has certain capability of not being scalable. So if you have a multiple device interacting together, then Simulink will, kind of explode because it cannot do that. So everything is possible up to certain extent.
Hmm. Sir, I asked this question because we do not have exposure of OpenDSS, so that's why I asked.
Oh, okay, yeah, yeah. OpenDSS is actually free and open source, so that's why we're using OpenDSS here, because it is designed and has a library for all the DR control, and another one is GridLabD. So it's definitely better than MATLAB because in MATLAB you have to start from scratch, and even though there is some library in MATLAB also for distribution system and DRs, but OpenDSS is, I think, at least we think that's much better. It has come and customized for the power distribution system.
All right, sir. Thank you.
Yeah.
So thank you, Professor Anurag Srivastava. Thank you so much for the today's session. It was very informative, as well as you have already, given the content how we are going to cover this course in 10 days. So again, I would like to say we are unlucky that you are not in IT Jammu campus, because our Dr. Sir is also missing you, because he's also work in cyber physical system in some of the area, and we are also sharing one of the students with him. So no problem, sir. Thank you so much, and have a good day today, and hopefully we will meet tomorrow.
Yeah, thank you. Yeah, I think I missed being there, but like you said, I will plan another workshop or sometime. I'll
Absolutely, absolutely, sir. Absolutely. So have a good day, sir. Take care.
All right,
And
thank you. Yeah,
okay, so
see
all
you
the
tomorrow.
participants, thank you so much. Have a good day. And good night to the Indian, as well as good morning to again to Anurag sir. Thank you so much.
Thank
Thank you,
you.
sir. Thank you so much. Good night.